So guys, here are some of the propagation delay calculations in a PCB which every high-speed design engineer must know. So the first thing, we will start with a signal where, let us assume, we propagate the signal over air. So we already read this in our science in school that the signal travels in air vacuum at a speed of 3 into 10 power 8 meters per second or 3 into 10 power 10 centimeters per second, right? That's the speed of the signal in air. Now if you convert it into inches per nanosecond, why we are converting to inches per nanosecond is generally in PCB terminology we use inches as the trace length, and then the rise time fall time we got used to reading in terms of nanoseconds. Okay, so 11.8 inches per nanosecond is the speed of the signal in air. Now if you want to calculate the propagation delay, it is just the inversion of speed. So when you want to calculate the propagation delay of the same signal in air, it is 1 by 11.8 inches per nanosecond, which comes to around 84.7 picoseconds per inch. So that means if a signal travels 1 inch of distance, the delay that is caused in air is 84.7 picoseconds. Now we have talked about the propagation of the signal in the air. Now our signals propagate over the PCB traces, right? These PCB traces can be internal as well as external. So what do you mean by internal? Internal means the inner layers of the PCB. So we will definitely have multi-layer PCBs, right, for high-speed signals, where you want to route the signals in the inner layers considering the EMI issues, right? Now the signals can also route over the top layer and the bottom layer, where they break out from the driver or connected to the receiver or to any connectors which are placed either on the top or the bottom. Now if you want to calculate the propagation delay in a PCB, you have to do it in two ways. For the signals which are traveling in the inner layers, which is called a strip line configuration, and for the signals traveling on the outer layers, which is a microstrip configuration. So for strip line configuration, propagation delay in strip line is given by the propagation delay of the signal in air into square root of the dielectric constant. So dielectric constant, let us assume if it is 4, let us take it as a 4. In that case, to just easily calculate, it comes around, the propagation delay comes around 170 picoseconds per inch in a PCB. So you can see here in air, the signals travel faster than the PCB. Now this is the strip line configuration. If you want to do for a microstrip, it is 84.7 into epsilon effective. What is this epsilon effective? Now strip line, we know that this is the traces between the two layers internal to the PCB, right? Whereas microstrip, you have one layer as reference below and the top you have a air. So the dielectric constant will be the effective dielectric constant calculated between the air and the dielectric constant of the PCB material. So that is calculated by epsilon effective, which is calculated using 0.64 into epsilon r plus 0.36. So this is the effective dielectric constant. So if you calculate this, you will get the effective dielectric constant. So two things here. When we have to calculate the delays that occur in a PCB for a FR4, we can conveniently assume that for a FR4 material PCB which is used for propagating the signal, in that case the delay associated is 170 picoseconds per inch, assuming that dielectric constant is 4. Okay, so a very important assumption. And if you see anywhere, most of the assumptions when people talk about propagation delay in FR4, they consider it as 170 picoseconds per inch and go ahead. So this is where the entire calculations come from, and every design engineer must be knowing this, uh, and then having them handy, and they must be able to calculate whenever required. A very important knowledge required for high speed designs. Thank you.